So that, yeah, it makes sense mathematically, but of course physically this is a very, very unusual situation. And in fact, this is not something we'll have time to do, but if you consider a potential well, which suppose in a radius, so suppose that this is not x, but the radius, okay, r. So it's a radial, it's a, if you like it in a two-dimension, it's a rotationally symmetric potential. Okay, suppose this is your potential. Okay, so this is, okay. Okay, suppose this is your potential, and you're looking for like solutions which have energy like this. Okay, so it's less than the energy of the particle of the total, the height of the potential, but there's a region where this is the potential energy becomes less. So it's kind of a, so if you solve quantum mechanics, if you find the wave function, you can show, not very hard, that here you will have, you will basically have a wave function like that, right? Just from our intuition about what we discussed in the one-dimensional potential problem, right? And so essentially, but then it goes out and it becomes, it becomes a, it becomes some sort of an oscillatory potential outside. This is not accurate, by the way, because the potential energy is changing. So what this shows is that even though the energy of the particle is less than the potential barrier, because of the wave nature, a small part of the wave function leaks out. And that means that given some time, the bound particles here will escape the potential. Okay? So this is actually a model for radioactive decay, where you can think of this potential well as the nucleus. Okay, this is a very crude approximation to the nucleus. And particles inside the nucleus are trapped in some sort of potential well, but once in a while, one of them will escape. And when you do this analysis, what you will find is that the probability of escaping depends exponentially, I forget what the constant is, on V naught. Okay? On this. So if you change this V naught even so slightly, which depends on the nuclear number and stuff like that, okay? On Z, and this is a function of Z, not a very complicated function. So if you change, the number of atoms, so the atomic number ever so slightly, the probability of the particle escaping or the nucleus decay changes a lot because the dependence is exponential. So this very crude model was able to explain the extremely wide variety of lifetime that we see in nuclear physics. Okay, in nuclear physics, the lifetime of nuclei is just, varies wildly. Some of them seems like stable. It seems to have infinite lifetime. Others are like, matter of minutes, and stuff like that. Okay, so this is this is an example where this is called a tunneling phenomenon. Okay, this is called the quantum tunneling. Okay, so this has an important, and this is another example where the fact that the particle doesn't have energy greater than the potential barrier, it still manages to leak out because of the wave nature. And quantum tunneling is also used in the electron scanning microscope, okay? Electron scanning microscope. And what it does is that, sorry, microscope should be. And what it does is that you have some sort of tip, and you have a surface, and this is kind of a, there are some free electrons, and this is a potential barrier, but there is some probability that the electron will escape to the surface, and if it does, then it creates a current. But the probability depends on how far the surface is. So if the surface is nearby, the probability increases. So by running this tip on a surface, you can actually find out what the atomic distribution is of the surface. Okay, so this is another example of quantum tunneling.